we're going to be talking about the min-distance problems. These are the problems I like to put on the test. But I've got a segment here, right, that we have to calculate the distance of. If you know, it's Pythagorean theorem. But if I draw over and down to a right angle, the coordinates of this last point are x2, y1. And of course, we get our delta y as y2 minus y1, and our delta x as x2 minus x1, right? And so then we know d squared, right, is delta y squared plus delta x squared, or better yet, d is the square root of delta y squared plus delta x squared. And I'll call that now my function d of xy. Oops, I better not do that. D is the square root of y2 minus y1 quantity squared plus x2 minus x1 quantity squared. And you can see in there that this is my function with two variables. This is my expression with two variables, right? It actually has four variables, but we're gonna turn it into two, okay? So this is the one I want at all times. I want to know this formula because I'm going to use it every time it's the thing I'm going to minimize, right? If I'm trying to find a minimized distance, I want this as my function. Now, it's going to change a little bit once we put the information in. And so you'll see here, and I'm going to write that down again, okay? You'll see here, I'm going to say I've got the function y equals the square root of x. And that is my equation. That is my equation. The function I give you, that's going to be my equation. And I want the min distance, let's say, from 1, 0 to the curve. So the question is, what is the point on the curve? What should I call this purple point here? What should I call this red purple point here? It's unknown, right? I want to find the min distance from this point to the curve, but I don't know the point on the curve, so what should I call it? Yes, xy, or better yet, x square root of x, right? Because so that's when we're using that equation, right, to solve, to put everything in terms of x. Yes, you okay? Yep. So it's unknown, so definitely the x is an x coordinate. The y is a y coordinate, but we know y is the square root of x, so we're trying to get something all in x's, right? Okay, here comes my d of x now. D of x is my min distance, right? So I need y2 minus y1 quantity squared plus x2 minus x1 quantity squared. And there it is. So that's the setup for this min distance problem. Now the function's going to be different, the point's going to be different, et cetera, right? We'll do one in a second with the ellipse that's in the book. But this is typically the one I give you. Now, what do you know about this distance? What do you know about that gray segment? It's perpendicular to the tangent line on the curve. The shortest distance to any point is a straight line, right? So I'm not going to go to the wall on this angle. I'm going to go to the wall at a 90-degree angle, right? So we're always thinking it's going to be a perpendicular to the where we're headed to. Yes. Yeah, it would go to a different point, but still perpendicular to the curve, perpendicular to the tangent line. Yeah, that won't be the min distance. Yeah, but my segment would be different. The point it hits would be different. I've got to make sure. So you're saying, right? You're saying I've got a point instead of at 1, 0. I'm here. Again, it's got to get to a right. Exactly. Now this can be simplified, and it usually is helpful to do so. So it looks like I have x plus x squared minus 2x plus 1. So my distance that I'm trying to minimize finally ends up at x squared minus x plus 1. So I'm just trying to get a nice function to work with, right? All right, so the rest is the same, right? So find the derivative, find the critical value, answer the question, verify that you have a min distance. So how do we do there? I like to notice that when I do my derivative, I actually see the original distance formula in there, right? And I want to note that that distance cannot be 0, right? Why does that make sense? Why can that distance not be 0? Not on the curve, right? And it can't be maximized. That distance can't, there's no max distance that goes on forever, right? These distances will just keep getting longer and longer as I go. There's no max distance. No, the distance can't be 0, and there's no max distance. So our critical values only matters when the derivative is 0. So that means 2x minus 1 equals 0, or x equals 1/2, right? I have to find the point, I have to find the distance, I have to show it's minimized, right? So the point is what? It's 1/2 comma square root of 1/2, right? The distance, so 1/2 squared minus 1/2 plus 1. Now, when I do my d double prime, I'm going to use this version every time. So I got d prime as 2x over 2 times d. And I'm going to use a quotient rule to get, is everybody okay? Don't let me go too fast here. Slower. That's where the numerator of the derivative is zero, right? Or the denominator is zero. We already know the denominator can't be zero, right? But it's not the square root of x that's going to have a horizontal tangent. It's the distance formula. So watch what I mean. Because remember, it's the distance, and the distance is never zero. So look at my denominator again, right? You see my denominator. It's exactly my distance formula. And I know that distance can't be zero. Yeah. Yes, good. So first of all, let's make sure we're using all of our old kind of tools, right? I got f of x, or d of x, was the square root of x squared minus x plus 1, right? And you can see it's that low point. So I think, Tia, make sure I'm reading this correctly. You were thinking it would be where there's a horizontal tangent on the square root of x curve. But that curve is just getting me my endpoints of the segment. It's the distance formula I'm minimizing. That segment, right, that gray dashed line, that's my distance. I'm trying to get that minimized. Yeah. So what I graphed was this d of x function, and that one you saw looked almost parabolic, right? It's square root of a parabola. It just kind of straightens out the curve, makes it more like an absolute value, and obviously to hit a low point of the distance. Right, exactly. I gave it to you. I gave you 1, 0. I'll give you the curve. I'll give you a point. Exactly. So we figured out the numerator is equal to 0 at 1/2, right? And now I know my x value. That's the x value for the point. That's the x value for the distance. So I plug it into the curve, right, to get the point 1/2 square root of 2 over 2. I plug it in the distance to get square root of 3 over 2. And I still have to plug it into the second derivative, hoping to get what? So if it's going to be a min distance, right, what do you see? A smile or a frown? Smile. So what should I get out of my second derivative? Positive. Positive people smile. All right, quotient rule. Ready? Upstairs function is 2x minus 1. Derivative is 2. Downstairs function is 2 times d of x. Derivative is 2 times d prime of x. And then the downstairs squared is 4d squared x. It will be easier for you to do this in general than doing it with the whole distance formula, okay? So practice with it and see how you do with it. Also try it with the whole distance formula and see how messy it is. So d double prime of x is coming from 4dx minus 2 times 2x minus 1 times d prime of x all over 4d squared of x. We found a critical value of 1/2, right? But what do you notice here? Anything go away here? Well, d prime of 1/2 is the critical value. That's 0, right? So all of this is gone. D double prime of 1/2 is actually 4 times d of 1/2 over 4 times d squared of 1/2. Ah, well, 4's cancel, and one of the distances cancel. So I get 1 over d of 1/2. But I know the distance of 1/2, right? I already found it. It's square root of 3 over 2. So I get 2 over square root of 3, definitely positive, so who cares about rationalizing it? But I will. What was it, 1, 0? Yeah. This is not that easy at first, but you have to jump in there and try and mimic what I'm doing until you figure it out. Arsema? Yes. Where are you? Let me put numbers. Where are you? That's okay. I like never mind. How we doing? Say again? Yeah, so remember, conclusion is, oh, zoom in on it, sorry. Yeah, sorry. Remember, conclusion, we want to find all of the things that they were asking for. What's the min distance? What's the point? Right? Yeah, you should. Yeah, I did, kind of here. Right here, right? How we doing? We okay? Just writing. A lot of writing in chapter 4. Sorry, in chapter 5 there isn't. In chapter 5, we are really prepping you for Calc 2. I am going to prep you for Calc 2, so it doesn't matter which teacher you take it from. Doesn't matter if you take it at Howard, University of Maryland, any campus here. If you really know chapter 3 and chapter 5, you will be ready for Calc 2. Okay? All right, let's look at the problem from the book. It says number 15, find the points on the ellipse that are farthest away from 1, 0. So we certainly need a picture of what the hell is going on here. And it's a lot easier with Desmos. I can draw this ellipse on my calculator by solving for y, and I'll get a plus or minus square root. And I can put y1 in as the positive square root and y2 in as the negative square root. But let's go right away to Desmos. 4x squared, plus y squared equals 4. There's my ellipse. And I want to find the 2 points that are farthest away from 1, 0. So there's 2 points that are furthest away from that 1 point on the ellipse to 2 points on the ellipse. Did I do that right? Let me make sure I read it right. Yep, furthest away from the point 1, 0. So you can kind of imagine it, right? This is a 4.6, number 15. And I've got my ellipse here. And I'm trying to find 2 points on the ellipse that are furthest away. Right? So this would be congruent to this. But let's just find a positive one just to make it a little bit easier. Right? Let's just find this 1 point. So what do we know? We know this point is 1, 0. The other point is x comma what? Well, y, of course, right? X squared, 4x squared plus y squared equals 4. So y squared equals 4 minus 4x squared. Y is the positive. Remember, I wanted the positive one. And I certainly could make that 2 square roots of 1 minus x squared. So that's 1 point, and the other point is 1, 0. How are we doing? Everybody comfortable here? Anybody not comfortable? Anybody hear me? Can anyone hear me? Okay, you can hear me. Okay, whatever. Distance formula, obviously, right? So what do I get? It looks like I get 2 times square root of 1 minus x squared minus 0 quantity squared plus x minus 1 quantity squared. Very similar to the last problem. So we get negative 3x squared minus 2x plus 5. Okay? So d prime of x is what? Negative 6x minus 2 all over 2 square roots. I like just to keep it as d of x. So it looks like I get what as my critical value? One third? Negative one third, right? The so if we look at right, if we look at the situation, right? Remember, I'm trying to find the max distance here. D of x can equal 0 in this case because the point is on the curve. But obviously, if I let d of x be 0, it's going to give me the same point, right? And I'm going to get a distance of 0. So I don't really care about that denominator equal to 0. So I want to look at this ellipse here. I want to put in my x equals negative one third and see if it's kind of making sense that that's where it's going to hit my min distance. My max distance, sorry. This one's not going to be perpendicular to the tangent line, okay? But we know when we're doing our min distance, we're trying to walk a perpendicular, right? But the max distance in this case is not going to be perpendicular to the tangent line. All right, what's left to show? We want to find d double prime of negative one third. We want to find d prime of one third. That we know already. We want to find d of one third. And we want to find our xy, right? Oh, sorry, of negative one third every time. Well, d double prime is pretty quick, right? I'm using this, I'm using a quotient rule. Negative 6x minus 2, derivative of that is negative 6. 2d of x is derivative of that 2d prime of x. And of course I get 4d squared x again. And that's going to be the same every time. Same idea every time. So I get negative 12 d of x plus 2 times 6x minus 2 plus 2, sorry, d prime of x all over 4d squared of x. Yeah, I did. I factored out the negative and canceled it. Yep. So this one gets the negative. Yeah. Now we already know d prime of negative one third is 0, right? So we certainly know the same thing's going to happen here. D double prime of x, of negative one third is what? It's going to be negative 3 over d of x. And I can already tell the distance is not negative, right? So this is going to be negative. And negative people frown, right? So if I'm looking at that frowning face, I know I'm talking about a maximum distance. Yep. So I want to find the distance. Sorry, I want to find d of 1/3, negative 1/3. So I found the second derivative was negative. I know the first derivative is 0. I know the point, the distance exists, so the point on the curve exists, right? So, and all I have to do is find the point on the curve. So negative 1/3, 4 times 1/3 squared plus y squared equals 4, right? Yeah. Oops, I shouldn't be writing that as a point. I'm just solving for y in my ellipse formula. So the point is negative 1/3, 4 square roots of 2 all over 3. Finding the max distance, right, from that point to the curve. Yep, so let me put that point on. Negative 1/3, oops, comma, 4 square roots of 2 all over 3. There it is. Now, nothing I'm doing do you need to copy. You have a distance formula, plug the negative 1/3 in there. You have a function, like plug the negative 1/3 in there, find the y. You can find the derivative, you can find the second derivative, right? All right, I want to do a little bit more work, and then we're going to break early in case anybody wants to talk to me, okay? Let me stop my recording because I'm going to do all of this again.